All right, welcome to this explainer. Today, we're tackling something that is literally reshaping how artificial intelligence operates out in the real world, LLM fine-tuning. If you've ever found yourself wondering how a massive, kind of general-purpose AI suddenly transforms into a hyper-focused medical assistant or a razor-sharp legal analyst, well, you're in exactly the right place. We're going to dive right into this and explore exactly how we can adapt pre-trained models for highly specialized enterprise tasks.
So first off, why does LLM fine-tuning even matter? Well, out-of-the-box base models are undeniably powerful, right? They've practically read the entire internet, and they have this incredible grasp of language. But for an organization, that's just not enough. You don't just want a generic conversationalist. You want an AI tailored to your specific domain, speaking in your specific style, and strictly adhering to your specific behaviors. And that is exactly the magic we unlock through fine-tuning.
Here's our roadmap for today. We'll be covering what fine-tuning actually is, the core techniques, parameter-efficient methods, the major challenges you'll face, how it stacks up against RAG, and finally, a practical workflow to get you started.
Okay, let's start right at the foundation with Section 1, what is LLM fine-tuning?
Think of initial pre-training as the phase where a model learns general language patterns from massive, sprawling text collections. Fine-tuning, on the other hand, takes that already trained model and tweaks it using a highly specific, focused set of information. It essentially gives that raw, unfocused power a specific direction, sharpening the model's abilities for specialized jobs like analyzing data, answering complex questions, or providing customer support.
The whole journey is actually pretty straightforward. You start with Step 1, your pre-trained LLM. And Step 2, you introduce your targeted training data. This is your fine-tuning phase. And finally, out comes Step 3, a specialized model that understands exactly what you need it to do. It's kind of like sending a smart college graduate to medical school. They already know how to learn and communicate. Now you're just teaching them the highly specific practice of medicine.
Which brings us to Section 2, core fine-tuning techniques. There's a bit of an alphabet soup in the industry right now, so let's break down the major approaches.
First up is supervised fine-tuning, or SFT. This is where you train the model on labeled datasets where the correct outputs are already known. You're basically feeding the model prompts and instructions paired with the exact right answers. A really fantastic example from our source material is Stanford's Alpaca project. They used SFT on a 7 billion parameter model using just 52,000 instruction-following examples. And the cost? Under $600. That is practically pocket change in the AI world, and the result was a model that showed behavior comparable to much, much larger systems.
Next, we have RLHF, which stands for Reinforcement Learning from Human Feedback. This technique is really interesting because it uses human preferences as a reward signal. It's essentially a three-step dance. First, you do the supervised fine-tuning we just talked about. Then, you train a separate reward model based on how humans rank different responses. Finally, you optimize the main model's policy using a complex algorithm called proximal policy optimization. It's highly effective at reducing toxic outputs and dramatically improving truthfulness.
Now, RLHF is incredibly powerful, but it's also quite complex to set up. That leads us to DPO, or Direct Preference Optimization. DPO actually skips that separate reward model entirely. Instead, it directly optimizes the language model using that same preference data. The research shows that DPO matches and sometimes even exceeds RLHF performance, but it's substantially simpler to implement. In fact, this is the exact method behind powerful models like Zephyr 7B.
When you put these techniques side by side, a really cohesive picture starts to emerge. SFT uses labeled demonstrations to teach direct instruction following. RLHF relies on human rankings to align the model with complex human preferences safely. And DPO uses that same preference data, but it adapts the model directly, cutting out the middleman to achieve that exact same safe, aligned outcome, but with a much cleaner, simpler implementation.
Now let's talk about hardware, which brings us to Section 3, parameter-efficient fine-tuning, or PFT.
Trying to rewrite a model's entire architecture, which is what we call full fine-tuning, is incredibly expensive and requires massive computing power. Parameter-efficient fine-tuning sidesteps this massive hurdle by adjusting only a tiny fraction of the parameters, leaving the vast majority of the original model totally intact. The result? You can suddenly run these heavy customizations on standard consumer hardware. It literally democratizes AI development.
The absolute rock star of PEF methods right now is LoRA, or low-rank adaptation. LoRA freezes the original pre-trained model weights and then injects tiny, trainable low-rank matrices right into the model's layers. Just to put that into perspective, Look at these stats from the source. For a Llama 3.18b model, LoRA uses just 0.06% trainable parameters. Let that sink in. And it requires only 57% of the memory compared to a full update. Because these injected matrices are so small, you can actually switch between completely different tasks efficiently just by swapping out these tiny files.
And LoRA has evolved incredibly fast. We now have QLoRA, which adds quantization into the mix, which is essentially compressing the numbers the computer works with to save space. QLoRA introduces 4-bit normal float and double quantization. That innovation alone enabled fine-tuning a massive 65 billion parameter model on a single 48GB GPU. That is huge! And then there's QA-LoRA, which improves on this even further with end-to-end INT4 quantization, achieving even better accuracy in really aggressive compression scenarios. Of course, it isn't always smooth sailing, right? Let's move to Section 4, the major challenges. There are 4 main hurdles you've got to watch out for. First is overfitting. This is when your model rigidly memorizes your training data, but suddenly can't adapt to new, unseen examples. Second is data quality. Remember that alpaca project? A small, brilliant dataset is vastly superior to a large, messy one. Quality absolutely outranks volume. Third is catastrophic forgetting, which is exactly what it sounds like. The model literally gets AI amnesia and forgets its old capabilities while it's learning new ones. And finally, the alignment tax. Sometimes adding strict safety guardrails can actually reduce the model's raw performance on standard tasks.
Overcoming those challenges brings us to what is probably the most critical architectural decision you'll make. Section 5. Fine-tuning versus RAG.
RAG stands for Retrieval Augmented Generation. So what's the real difference here? Well, fine-tuning deeply embeds static domain expertise and specific styling directly into the model's internal parameters. It fundamentally changes the model. RAG, on the other hand, doesn't retrain the model at all. Instead, it goes out and fetches external, up-to-date facts from a database right when you ask a question. To put it simply, fine-tuning teaches the model how to speak, while RAG gives the model verified current facts to speak about.
So how do you choose? Well, you should go with fine-tuning when you absolutely need a specific style or tone. Your core knowledge is relatively static, and you have access to great, high-quality labeled data. You choose RAG when your information changes all the time, or when you strictly need verifiable source attribution, like footnotes pointing to exactly where an answer came from. But actually, here's the best part. The source notes that many of the best enterprise systems combine both. Use a fine-tuned model to get that perfect domain tone, and you connect it to a RAG system to feed it fresh, verifiable facts. It's the ultimate combo.
Okay, so how do we actually do all this? Let's jump into our final section, a practical workflow.
The workflow starts at Step 1 with dataset preparation, carefully structuring those high-quality instruction-response pairs. Step 2 is choosing your approach. If you're just starting out, our source highly recommends using QLoRA and supervised fine-tuning. Step 3 is training configuration, where you set things like your learning rates and batch sizes. Step 4 is running the actual fine-tuning, usually leveraging open-source tools like Hugging Face PEFT. And finally, Steps 5 and 6 are evaluation and refinement. The golden rule here: start simple with smaller models, test rigorously, and let your evaluations guide your next iteration.
And honestly, the results of this workflow in the real world are just astonishing. In healthcare, fine-tuned models like Metatron are automating tedious documentation, potentially cutting charting time by up to 50%. In the legal sector, they are mastering contract review because they can deeply understand complex legal jargon. And in code generation, models like GPT-J achieved up to a 10% improvement in generating non-vulnerable code entirely through specialized fine-tuning.
So we've covered the core techniques, the massive efficiencies unlocked by LoRA and QLoRA, and the highly strategic choice between fine-tuning and RAG. The tools are open source, and as we've seen, you can even run them on consumer hardware. So I want to leave you with this final thought. Now that you know these techniques, what specific domain are you going to conquer by fine-tuning your very own specialized model? Thank you so much for joining this explainer, and we will catch you on the next one.